Hi, this is Roy Bolaños. Welcome to another edition of Power Electronics. In this video, I'm going to show how to calculate variations in your power supply due to second order effects. Now this is a very important subject. If you need a power supply that needs a precision supply, okay, let's say that your power supply that you're designing is supplying a let's say some kind of a instrument, a precision instrument. Okay. In my case, some of the power supplies that I do are supplying space hardware that are taking very precise measurements. Okay, and since you need a very precise supply, you want to be able to minimize those variations. Okay. And most of the variations typically come due to the error amp. Okay. And it's usually your op amp. The op amp that they're using. Okay. So basically the second order effects are from the op amp. Okay. And there are three basic parameters that you have to be aware of, and these you can find them in your data sheet of the part or the op amp that you're using. Okay, so the first parameter is VOS, which is the input voltage. Second is IB, which is the input bias current, and then you have IOS, which is your input bias offset current. Okay, so these are the basic parameters or op amp parameters that we're going to be taking a look at. Okay, and what we're going to try and do is we need to take into account these, understand them. Okay, and once we understand them, then we can try to minimize the effects, and I'll show you how to nullify at least one of them and minimize the other one. And then I'm going to try and see if we can model them or show you a method of modeling them both in SPICE, okay, and mathematical. And the reason that we do the mathematical is because then once you see the equation, we can see how to reduce the errors. Reduce the errors due to these parameters. Okay, so that's the topic. So I'm going to go ahead and define what VOS is. VOS is the input voltage offset. Basically, it's the voltage. It's VOS is equal to VP minus VN. So whatever voltage you measure here, let's say it's 10 millivolts, and then let's say this is 5 millivolts right there. Then the offset voltage is going to be 10 millivolts minus 5 millivolts, 5 millivolts. So you would have a VOS of 5 millivolts. So it's basically the difference in the voltage between the positive terminal, okay, represented by VP sub p, and the non-inverting terminal, the v sub n terminal. Okay, so we'll do that. The second is your input bias current, which is IB, and that's fairly simple. It's basically the average input bias current. So you can put a current probe around the non-inverting and the inverting, and you take a measurement. So you measure I sub n, and then you take I sub p. So you have two measurements, and you put them in this equation. Basically, you add them up, divide them by 2. So what you get is the average current. That would be IB. Okay, and that's represented by this equation. This is a very important equation, and we're going to use this equation. Okay, so we have that. So now we have input offset IOS, and that is the difference between the two inputs. In other words, these will never be matched. IN and IP, well, they're always going to be a little bit of a difference. Okay, so the equation or the definition of IOS is basically IP minus IN. So the difference, it's basically the difference between the currents. So once we have these two equations, this is the first equation, second equation. Okay, so we're pretty much set. So you have VOS, second equation, and the third equation. And the ones that we're going to concentrate right now is these two. Okay, because this one is very simple to model. In fact, I'll go ahead and just say it right here. To model it, at least in Spice, if you have your terminal, what you do is you add a voltage source, and you try to label it like so, VOS. So this would be the model. And the op amp that you use an ideal model. An ideal model will have no IB will be 0, IOS will be 0, and VOS will be 0. So you use an ideal model and you add a parameter, in this case VOS. Okay, so now we've done this. We already showed what the model would be. You add just a little power source in series with the positive to going on the left side. Yeah, left side. Okay. And then with these two equations, IB and IOS, you basically solve for IP, and this one you also solve for IP. So in this case, once you solve for IP, you set them equal to each other. So in this case, let's see, IP, let's see if I can do this. It would be 2 IB minus IN. And then this one would be IOS right, plus in. So now these two are equal. Now you solve for in, and you get that equation. And then you do the opposite. Then you solve for in, and then solve for IP, and then you get this equation. So basically these are the two equations, or the equation that is very important. Because this is the one equation that we're going to model in Spice. And then we're going to do a mathematical model. Okay, so now that we have our equations, we can add those. We're ready to make a model, a Spice model. Okay, and we're going to use an ideal op-amp. So this is supposed to be ideal. And ideal because you want the ideal for it to have no bias current, no offset current. So basically you want these to be 0 internally. Okay, but you're adding these externally. So in this case we're going to add VOS. Like you see here, you insert a VOS, just like I had mentioned here, that you add VOS, you insert into the positive node, you insert a VOS signal with a positive on the left and right, and this will be random. In other words, this can change opposite. In other words, it can go from a negative to a positive. So basically we're going to have two answers, okay, or it gives you a range basically. Now to model the in, which is shown here, this is going to be a current source. Okay, and this is the current source. Okay, so we draw a current source going into the node, and then the other is connected to ground. So basically you're gonna have current going in this direction, and that's going to be in. Okay, and then you also do the same here. You add another current source from ground to the positive terminal, so you'll have current flowing in this direction. So this would be IP. Okay, now remember, in and IP are these terms. Okay, so this is what you do in Spice as well. So in this case I'm using a 12-volt supply. This is a 12-volt supply. Okay, or close to 12 volts. Okay, and then this is a ideal op-amp. It's a op-amp function. Basically the impedance is infinite, or very high, and gain is very high, and I guess it doesn't have VOS or a bias current or the offset. Okay, so in this case, if you notice right here, I put a voltage source and put the curly brackets, and then I type in VOS and close brackets, and then I put a current source here. Okay, I'll go to the enable and I type in the curly brackets. So IB minus parentheses IOS divided by 2 close parentheses close brackets. Okay, so I'm defining it here. Once I define, or I put this definition, then I come up here and I define what Ibias is. I go to the text, I put dot param, which is a splice directive, and then I define IB equals 1 micro. So that's what I just told it, that the bias current is going to be 1 micro, and then I define IOS as 10 nano. Okay, and likewise I do the same thing over here with IB equals plus IOS divided by 2. Again, curly brackets and so forth. Okay, so now let me go ahead and run this, but let's assume, or let's get what the real measurement would be if this is ideal, and let's assume that these are extremely small. Let's say that they're in the pico range, which would be almost negligible. But let's do a 1p. Let's go a femto here and a femto here. Okay, femto. So this would be the best results that we could expect or would expect. Okay, so we look at the voltage and it says 12.02, but let's get a little bit more of a closer range, or a more accurate. And to get a more accurate measurement, we go to the output file. Let's see, the output file, and we look for Vout. Okay, so here is, I'll copy that, so I'll go ahead and put it here, paste. So let me, this is 12 point, so this is the best, most accurate measurement that we would get. Okay, so we're going to use that number. Okay, and we're going to go ahead and do some calculations, and we'll use that number to compare. Actually, I think I have it here. Okay, right there. Okay, so we've done that, and we'll come back and do some comparisons. Okay, so now now we have the splice model ready. So now we're going to use this equation, the ones that we just derived. Right here. Okay, we're going to use them to see what the voltage out would be with these parameters defined. Okay, so now we do a schematic, and this would be very representative of all power supplies, or most power supplies. They can all be broken down into this form, so to speak. Okay, so basically you would have a output voltage, and let me see if I can get both here. That way I don't want to confuse you all. So if I can put this together because this is critical in understanding this concept. Okay. What you want to do in this case, you want to represent or simplify this. So basically this here is basically this path. Okay, this can be neglected. You're just concerned with this path that goes through here and through here. Now, if you notice this here, you have a voltage divider network. Okay, and this is V out. So this point, you can think of it as this point, although it's not really. This, in this case, this is VTH. But there's a relationship between VTH and V out, but I'll show that representation or relationship. But to simplify or get it into this form, we do a Thevenin of these two resistors. So basically this resistor in parallel with this resistor will be this R top. So basically the R Thevenin is equal to 19K in parallel with the 4.99K. Okay, and that combination is actually 3958 ohms. Okay, but for the time being, this R Thevenin, I'm going to rename it and just say R top. Okay, so remember this R top is really equal to 3958, which is the parallel combination of the 19 and the 4.9, basically these two resistors. Okay, and then the bottom resistor is typically, the rule of thumb is whatever your impedance is looking back, or that the non-inverting sees is these two resistors. Whatever the impedance is, you make that resistor the same impedance. So basically this is R bot, that's R bot, and this one typically is going to be the same as R top. Basically it's a rule of thumb, and it's also going to be 3958, and you'll see why we make them. There's a reason that we try to make this and this equal. Okay, so I'm going to show that in a little bit. So anyway, so now we have that. Okay, so now we're ready to do the voltage Thevenin, or the KVL. So in this case, since the current is going in this direction, we label the polarity of the voltage drop. So we'll say that this is positive, this is negative. So the arrow is going to point to the negative direction, and then this here, since we said that we can put it here positive, we'll make this positive and we'll make this negative. So this would be your VOS. Instead of putting it in series, or actually we can put it in series. Let's do that. Let's do that. So I'll put a voltage source, and we'll put this negative, positive, and this is VOS, and we're going to assume that these are equal. Yeah, we'll say that basically Vn is equal to Vd. So basically you can think of it as shorted. Okay, so now with that we can say V out. Okay, oh I'm sorry, and then again, we continue with this. We label that positive, negative, and then positive and negative. Okay, so now we're ready. So we're going in that direction and then down. So this is V plus, and then this is positive IN times V R top, and then this is VOS plus or minus. And now it's plus or minus because it's a random. It's a random parameter. Meaning that they can, VOS can change due to temperature. So it can be positive or it can be negative. Okay. So it's really random depending on temperature and so forth. So we account for it with this plus or minus. And then we continue. Then this is negative IP times R, which is right there, and then negative V ref, okay, equals 0. Okay, so this is the equation, your KVL equation. Okay, so now once we have that, then what we do is we substitute these into there. Okay, and we substitute that into there. Basically we substitute that, and here we have the terms. This is for IN, this is for IP. Okay, and then after a little bit of algebra, we can separate the terms. So now, and we change this to V Thevenin, and I'm going to go ahead and do the statement. I had said that in this case this is VTH, is not V out. There is a relationship, and the relationship that I'm using is that VTH divided by V ref, and then V ideal and V actual. Actual is the one with the errors, and this ideal is what we calculated right here. Actually this would be the V ideal, and this would be your 2.5, and then this is what we're going to calculate, which is this here. Okay, hopefully that makes sense. Okay, so anyway, so let me go ahead and move this a little bit. It'll make sense in a little bit, or at least hopefully it makes sense. Okay, so now that we have this equation, which is very important, you're ready to make a little bit of sense of why we do what we do. Okay, so this term is going to give you the errors due to IB. Okay, but let's take a look at this. Okay, what's it saying? Well, this is the bias current times RB, R bot, which is a bottom resistance, minus R top. Okay, so you see what's happening? I hope you see it. Okay, remember I said here that rule of thumb, you want to make R bot the bottom impedance, and R top the top impedance, you want to make them equal. In this case it's 3958 R top, and the bottom is 3958, and we made them the same. They're equal. So if they're equal, then this term goes to 0. It gets cancelled. Okay, so that's why we use the rule of thumb. We make these two equal, this goes to 0, and basically you cancel the effects due to IB, which is really good to know. Okay, now we can also do the same thing over here. This term gives you the errors due to iOS. Okay, and in this case we don't have a negative, we have a positive here, so we don't have the cancellation. Okay, but it tells us one thing, is that if R top plus R bot, if these two go up, then the errors due to iOS are also going to go up. So to minimize, you can minimize the errors by making R top and R bot low, or you lower them as low as possible. Okay, so that's how you minimize it. Try to use low impedance resistance or impedance around your op amp. Okay, and then this term is the third term, and this is basically your VOS. There's nothing that you really can do as far as changing resistors. The only thing that you can do is use a better op amp. Okay, alrighty, so now let's use some numbers. Let's use some numbers, and since we're using the same resistance, we're going to go ahead and neglect this. So we're just going to say that it's iOS to R top plus R bot, and in this case I'm gonna, the way I label it, I'll go ahead and put VOS plus VREF. Okay, so we're going to use that equation, and I'm going to use VOS in our example, and then I'm going to use IB of 1 micro amp, and then iOS 100 nano. Okay, so in this case it's 100 nano divided by 2, and then this is, I believe it, what was it that I said, 3958 yeah, 58 ohms plus 3958 minus 10 millivolts, and then VREF is this voltage, VREF 2.5 volts. Okay, so let's see if we can see what kind of we get. So basically it's going to be 50, let's see if I can clear this, 50 negative 9 times open parentheses 3958 plus 3958 close parentheses, and we get 395, 395.5 microvolts. Let's see. Yeah, no, 5.8. Okay, that's what this is. VTH. Okay. Minus 10 millivolts plus 2.5 volts. Okay, so we're going to get a VTH. Okay, plus 0.01 plus 2.5. Okay, so we get a voltage of 11.9728 2849. Okay, so is that what I got? Let's see. Oh, I'm sorry, I did not get that. Okay, I got this voltage. Hang on. Let me erase that. This is wrong. Sorry about that. Let me do this again. Okay, let me clear it. It's actually 2.5 minus 0.01, right? Is there a minus over here? I don't think so. Yeah, there's no minus. Okay, so we're going to say plus 395.8 exponent negative 6 equals, okay, let's see if I get this right. Let me see if I can put this together. And that's not what I wanted. So put it right here. Okay, is 2.49093958. Ooh, 5.8. Okay, so we're not done yet. Okay, so this is the intermediate answer. Let me see if I can go back. And I said there's a relationship. Okay, so I said that there's VTH and VREF, and then V ideal, and then this is V actual. Okay, so let's do that. Now we have this VTH, which is 2.490398. Okay, and then this is 2.5 volts, which is a reference. Okay, we're there that far. And then we said that the ideal voltage, let's see, is 1, 2. In other words, this is the ideal voltage if you don't have any errors. Okay, so now this is the actual voltage due to the parameters. Okay, so we're going to do 12.0190236 and then this is 2.4903958, 2.5 volts. Okay, and let's see what we get. Okay, just bear with me. I'm getting there. Okay, so we're going to say 12.0190236 times parentheses 2.4903958 divided by 2.5 close parentheses, and we get 1197.28 50.35. So that's what we should see when we do the simulation, or at least close to it. Okay, so that's the voltage that we see now. So now let's set this to 10 millivolts. This is 1 micro, and then we'll set this to 100 nano. Okay, and we'll close this as the previous answer. Okay, so go to Tools, Browse, the output, and we go to Out. Here is Out. We'll copy. And okay, so basically, let's see how close. Okay, so this is basically 11.972877. So it's accurate up to that. I say that's pretty good when we can get this type of accuracy. Okay, so for all of this in purpose, this and this you can consider a match. Okay, so anyway, that's how you can characterize your power supplies. This is especially more important as you use higher voltages. Especially if you have voltages in the thousands. Okay, thousands of volts from, let's say, 1 kV, 10 kV. Okay, then the errors get amplified. Okay, and when you're dealing with these types of voltages, then you have to make this type of analysis. That way you can ensure that you can keep your the errors due to the second order effects down to a minimum. Anyway, I think that's enough of this. It's a very important skill to be able to do this. It's something that I use at work, typically on a fairly common base. And not only can you use this technique for high voltage, you can use it for any precision measurement that involves a op-amp. You can use this technique. If you find this video informative, please share, subscribe, and give me a thumbs up. And if you have any questions or comments, you can email them to my email, which will be listed on my website or YouTube, or you can send them to my email at rbola35618 at AOL.com. Again, thank you for watching. Bye.